So for partial fraction decomposition, we're going to use this method to integrate rational expressions. But number one, let's review a little bit of the basics of rational expressions. Essentially, what we used to do back in intermediate algebra, which is, well, you got to simplify these two fractions, you know, so, and well, we'll see how. So, whenever we have different denominators, you know, like with just pure numbers, like 1/2 plus 1/3, this is not 2/5. We don't just add the denominators and add the numerators. We can do that with the numerators as long as both denominators are the same. In this case, well, multiply by those missing factors. In this case, 3 and 3, 2 and 2. And now the new denominator should be 6. 3 times 1, which is 3. 1 times 2, which is 2. 3 plus 2, that's 5/6. And of course, we did that with rational expressions involving x's, or any variable rather. And in this case, well, we want to simplify this, but in this case, we don't have the same denominator. If both of these were x minus 3's or x minus 2, then put them together, just combine the numerators by the indicated operation, which in this case is subtraction. So no, in this case, we need to multiply by missing factors. I'm going to leave a space to leave those to figure out those missing factors. And in this case, to multiply numerator and denominator by x minus 2. And for the second term, to multiply numerator and denominator by x minus 3. Alright, so now that we have the same denominator, we may write x minus 3, x minus 2, or in any order, that's fine. Ultimately, it's multiplication. 2 times 4 is the same as 4 times 2, ultimately. And then from here, we're going to end up multiplying across 3 times x minus 2 minus 2 times x minus 3. So we're done with the denominator. Let's simplify the numerator. Alright? So let's distribute the coefficient for every single term. And that's going to give us a 6x minus, no, not 6x, 3x minus 6. Be careful with the negative sign over here. That's negative 2x. And negative times a negative is positive 6. Alright? And the whole thing divided by x minus 3, x minus 2. So all we have to do is combine like terms in the numerator. Notice the 6's cancel because they are opposites in sign. So all we do is 3x minus 2x, which is simply 1x, or just x. And final answer. So that's intermediate algebra, right? That's what you learned back then, whether you took it in high school or whether you took Math 72 here at Southwestern. Well, it depends. Okay, so partial fraction decomposition is to do the reverse of what we just did. We're given this a big, funky, condensed fraction. We need to rewrite it in simpler fractions. That is partial fractions. All right. So, and well, of course, okay, let's practice on that. Let's see how do we do this backwards process. All right. So on the one hand, we have this x over x squared minus 5x plus 6, which I'm going to rewrite as x over the factor form. We can factor this using the double bubble method. Factors of 6 that add up to negative 5. 2 and negative 3. Actually, both negatives, right? Because both negatives will give us a positive product, and the addition of two negatives will make a number even more negative, right? All right, what do we do from here? Well, how many factors do we have in the denominator? 2. We're going to write 2 different fractions. Ignore the x that we have here. Even if you had something like x to the 7 plus 5x cubed, ignore it. So we're going to write some letter a over x minus 2 plus b over x minus 3. All right? And we will use algebra to figure out those 2 values. So what I'm going to do here, I'm going to take a side trip. Essentially, I'm going to rewrite this whole thing. So let me write this. So x over x minus 2, x plus 3, x minus 3 equals to a over x minus 2 plus b over x minus 3. So we're going to treat this like an equation. We are going to write as a simpler version of the equation by multiplying both sides by the least common denominator. That's also intermediate algebra. When you went over this kind of equation, rational equation, the first thing you do is multiply both sides by the LCD to clear the denominators and have a simpler equation, whether this ended up being a quadratic equation or a linear equation or even a cubic equation that could be factored using, I don't know, maybe a difference or sum of cubes, or what else, something like factor by grouping, well, all the different methods. So let's multiply by the least common denominator. That is the quantity that will divide both x minus 2 and x minus 3. And that least common denominator happens to be the product of these two, x minus 2, x minus 3. Well, what's going to happen here? Well, so on the one hand, when we distribute, these two are going to cancel, leaving us with simply x on the left-hand side. When we notice what's going to happen here when we distribute these two right here. So when we do that, multiply this with the first term. Notice how the x minus 2's are going to cancel, leaving us with a times x minus 3. Do we all agree with this? All right. So that's equal to a times x minus 3. Using the same approach, distribute over the second term. See how the x minus 3's get canceled, leaving us with b times x minus 2. And that's b times x minus 2. And this equation is a lot simpler, and this is what we usually call our basic equation. This basic equation is used to find the values of a and b that decompose that funky looking rational expression into the sum or difference, perhaps it's possible, of partial fractions or simple fractions. Now, how do we deal with this equation? So, yes?
Can we treat a and b as constants?
Yes.
Okay. So you just put both integrals on both equations.
Yes, later when we integrate this, yes, we'll get back to put those, yes. Now, notice we have one equation, but ultimately like 3 unknowns. We have x, a, and b as unknowns. Now, there's a way around to find a really good way around that works with this type of equations, because ultimately we don't care about x. What we care is about those a and b. However, what happens if for x equals to 3? Notice how if we plug in a 3 on the first term, that gets zeroed out, and here we get another number, and we will be able to find b. So in this case, we can plug in our favorite value of x as long as we plug it in anywhere on one side or and the others and on both sides of the equation. However, we would look for convenient values. Yeah, that's the keyword here. Convenient values that help us cancel out one term so we can find the other one, and then we're going to do the same for the other letter. So let's plug in x equals to 3 equals to a times x minus 3 plus b times x minus 2, which in this case x equals to 3. All right, this gets zeroed out, and 3 minus 2, that's 1. So 3 equals to 1 times b, which is simply b. All right, let's do the same for another value. Can you think of another convenient value so we can find now the value of a? X equals positive 2, because this would zero it out, right? So for x equals to 2, okay, let's write down a 2 equals to a times 2 minus 3 and plus b times 2 minus 2. Okay, let me write down that 2. Alright, so what is in this case? Well, that goes to 0. And 2 minus 3, isn't that negative 1? Negative a equals to 2, and a equals to negative 2. So we're done finding those constants a and b that will break this funky looking rational expression into two simpler ones. So let's go back to our original problem, where a equals negative 2 over x minus 2 plus 3 over x minus 3. Isn't that the same expression as before? It's just in the reverse order that I wrote it. Alright, so what I did with this exercise is to do one problem, putting it together, combining the fractions together, and now we're going to do the reverse to break it apart, which is the inverse process. And yes, I mean, typically inverse processes take longer than regular processes. So, and yes, it's not going to be the exception for partial fraction decomposition. Alright, so now we're going to integrate using partial fraction decomposition. Well, so integrate x over x squared minus 5x plus 6. Well, of course, we're not going to do the partial fraction decomposition. Again, we're just going to use the result from the previous part. That is the integral of what we got again. Let me do the positive first. 3 over x minus 3 minus 2 over x minus 2 with respect x. Alright. And then from here, let's split this into two integrals. 3 times the integral of dx over x minus 3 minus 2 times the integral of dx over x minus 2. And well, these two integrals are really simple to evaluate. For this one, you don't even need the u substitution. So 3ln x minus 3 minus 2ln x minus 2 plus c.
You have the absolute value.
Exactly, I did that on purpose. In some cases we need absolute values, which is, this one is the case because x minus 2 can output incidentally negative numbers, as opposed to something like x squared plus 4, regardless of the input, whether positive or negative, it's always positive. Alright? And this is pretty much final answer. Now, my MATLAB, it's a little bit crazy when it comes to final answers. I believe my MATLAB accepts these answers, but otherwise, my MATLAB, when you look at the view and example, they end up with condensing this into the product of or rather condensing it into a single logarithm. To do that, well, we need to use properties of logarithms. Remember the basketball rule? So the coefficient becomes the power, and From there, this is ln of x minus 3 cubed minus ln of x minus 2 squared plus c. And then they use another properties of logarithms, the one that says that the difference of two logs is one single log, but write the quotient of these two arguments. And that's final answer. But I'm not sure if it also takes this. I believe it should take the expanded version of the problem. Hopefully it does. I believe it does. All right. And well, that's our first problem in partial fraction decomposition. All right, let's have a look at the generalized way to describe this method. Okay, so what are the steps of decomposing this, n of x over d of x, where big N stands for numerator, big D stands for denominator, all right? Okay, if improper, divide, polynomial long division. What's an improper fraction? An improper fraction, it's a fraction that for improper means numerator is larger than the denominator or the same. Okay, so this is an improper fraction. Technically, this 4 over 4, which ends up being an integer, you can think of it as an improper fraction because it's no longer a fraction, it's an integer, right? So on those cases, we'll reduce to 1, and that's 1.5. Quotient plus remainder over divisor, that's the format when we divide numbers, all right? Well, polynomial long division, so that's the first step. The second step, factor the denominator, and here is where every single factoring technique will be used. All right. Now we need to write out our partial fraction decomposition. Well, if the factor is linear, the numerator of the partial fraction is constant. If we have repeated linear factors, then we need different partial fraction for every single power that repeats. I'm going to go a little bit more in depth to explain why do we do that later. If the factor is quadratic, then the numerator of the partial fraction is linear, and we're going to stop here with type of factor that we have. Of course, we may have integrals, like really funky looking integrals, in which we may end up with cubic irreducible, quartic irreducible, quintic irreducible, etc. But we're not going to go that deep. And of course, we would have, if we have cubic corresponds quadratic in the numerator. If, for example, 60, that is a 6 degree, we need a quintic in the denominator, and that's in a way to honor the spirit of the problem that we divide fractions. You know, we need to work with proper fractions. That is, the denominator is smaller than the numerator is smaller than the denominator. Well, that's for numbers. In terms of polynomials, it's about the degree of the numerator being smaller than the one in the denominator. Of course, I mean, I know that sounds like a lot of words for now, but you'll see how this works. Okay, so what do we have? Okay, we have another example right here. Let's integrate 2x minus 1 over 4x minus 9. Number 1, is this an improper fraction? That is, the degree of the numerator is equal or larger than that in the denominator? So now we can go to the next step, factor the denominator. How can we factor this one? All right. All right, so what's the form in the denominator? It's a difference of squares. Okay, how do we factor a difference of squares? It's like a double bubble, but with one plus and one minus. It's a product of conjugate binomials. That's how we call it. And well, in the first place, we write the quantity whose square is 4x squared. What's that quantity? 2x. And on the second place is 3. And the same 2x minus 3. All right. The next step is to write down the partial fractions. All right. And this is the step where we simply ignore that 2x minus 1. Don't even look at the numerator. Just focus on the denominators, because in this case we have two factors in the denominator. We will write two partial fractions. One for the denominator, 2x plus 3, and one with the denominator, 2x minus 3. All right. The next step, well, is to take a little side trip and figure out those constants a and b. All right. So I'm going to focus on these two quantities, the 2x minus 1 over the two factors and the partial fraction. I'm going to rewrite those below. 2x minus 1 over 2x plus 3 times 2x minus 3 equal to a over 2x plus 3 plus b over 2x minus 3. And again, actually, it doesn't matter the order. Either way, those constants will coincide to be the corresponding ones, whether you write a over 2x plus 3 plus b over 2x minus 3, or the reverse order, a over 2x minus 3 and this to be the 2x plus 3. It doesn't matter. So, well, we need to rewrite this equation into a simpler form. That is, by multiplying both sides by 2x plus 3, 2x minus 3, which happens to be the least common denominator. All right. So when we distribute these factors, let me show the distribution. Do you notice how this 2x plus 3, 2x minus 3 cancel these two also? Leaving us with simply 2x minus 1. All right, the denominators got canceled when we multiply this. If unsure how is that working, well, think of this 2 as over 1. All right. These are in the numerator, these are in the denominator, they just cancel like that. All right. So from here, let's do the same. Let's do the same distribution on the right hand side. Multiply these two factors in red. But notice how the 2x plus 3 will cancel that 2x plus 3, leaving us with a times 2x minus 3. Plus b times, do the same. See how this 2x minus 3 cancel that 2x minus 3? Leaving us with b times 2x plus 3. And what is this? Our basic equation. All right. This is an equation that looks a lot simpler that we're going to use to figure out those variables a and b that will split that funky looking rational expression into a sum or difference of two simpler expressions. All right. And well, again, we can plug in our favorite value of x as long as we plug it on every single instance of x on both sides of the equation. I mean, that's simply the principle of the equation, like thinking of a scale. Whatever you put on one side, you have to put it on the other side to keep it balanced, isn't it? So it's essentially the same. However, we are going to put on both sides of this scale the amount that is convenient, so we can cancel out one of the terms and we can figure out either a and b, actually both a and b. So let's think of the first one. What would be a good convenient value? All right, 1.5. How about we think about this in fractions? 1.5, is that 3/2? So we're going to have 2 times 3/2 minus 1 equals a times 2 times 3/2 minus 3 plus b times 2 times 3/2 plus 3. So that's 3/2, 3/2, 3/2. Okay, so let's simplify. Okay, these two's cancel. That's a 3 minus 1. And okay, this cancels 2 over 2, leaving us with simply 3. But 3 minus 3, what is that? So this zeroes out. And over here, 2 over 2 cancels, leaving us with 3 plus 3, which is 6. 3 minus 1 is 2. And b equals 3. Alright? Wait a minute. I believe I got something different. It's 1/3. Yeah, so that's what I meant. Yeah, so 2 over 6, which is 1/3. Yes, I was looking on my notes. So that's the first one. Okay, we already figured out letter B. We need to figure out A this time. We need to find a convenient value for X, so we can, in this case, cancel out the B term, and we can figure out A. What number can we use this time? Negative 3/2. All right. So for X equals negative 3/2. Okay, let's 2 times negative 3/2 minus 1 equals A times 2 times negative 3/2 minus 3 plus B times 2 times negative 3/2 plus 3. All right, so let's write down that negative 3/2. Okay. Let's simplify this. Okay, these two's cancel, but be careful because that's a negative number. That's a negative number, so that's negative 3 minus 1 equals, okay, these two's are going to get canceled, leaving us with negative 3, which we need to subtract this negative 3. Isn't that a negative 6? And over here, cancel these two's, and we're left with negative 3 plus 3. But because negative 3 plus 3 equals to 0, this gets zeroed out. Right? So let's simplify. Negative 3 minus 1, that's a negative 4, equals to negative 6a. And a equals 4 over 6, which reduces to 2/3. So we just got both coefficients a and b that will split this partial fraction. All right? So we may go back to the original problem, which is the integral problem. So that's the integral of a, which is 2/3 over 2x plus 3 plus b, which is 1/3 over 2x minus 3. And let's just split this one into two separate integrals. That's I'm going to do 2 over 3 dx over 2x plus 3 plus 1/3 integral of dx over 2x minus 3. And while these two are simple integrals to evaluate, if you want to show the u du for this part, that's fine. All we end up with is a factor of 1/2. So this will be 2/3 times 1/2 ln absolute value 2x plus 3 plus 1/3 times 1/2 ln of absolute value 2x minus 3 plus c. Alright, and let's simplify this. So these 2's cancel, leaving us with 1/3 ln 2x plus 3 plus 1/6 ln of 2x minus 3, absolute value of 2x minus 3. Plus c. Final answer. On the exam, you don't have to condense this into a single logarithmic expression. This is fine, and I hope, actually I don't think my MATLAB is very picky about it. I think this is fine for my MATLAB. Because, I mean, ultimately, these are equivalent expressions. Alright, so let's see, what do we have next?